January 1994 Northridge earthquake took scores of lives, but few realized that clear warning signals were detected by scientists in California just days before the actual shocks.
It seems that every time a significant earthquake strikes, someone steps forward to say, "I told you so." In this case, we know of two such someones. Rob Roth reports on a couple of not-so-mainstream scientists and on radio waves, shifting tides, and missing pets.
The Northridge earthquake surprised millions of people, but it didn't surprise Jack Coles of San Jose. In fact, he predicted it.
When the quake signal came in, I knew that there was definitely a quake coming.
Coles, a former electronics salesman, runs what he calls the early warning detection network out of his trailer home. He claims movements deep within the earth compress underground quartz deposits, which then emit radio signals. By monitoring those waves with special equipment, he says he can predict earthquakes with 50% accuracy. 4 days before the Northridge quake, Cole says he saw an unusual pattern. 2 days before the quake, Cole sent faxes to Channel 2 and other media that on January 17th, a quake larger than 6.0 would strike Southern California between 3 and 6 in the morning. On the 17th, a 6.6 quake hit at 4:31 a.m. He says he predicted the Loma Prieta earthquake and others in California the same way.
All 20 quakes in the Bay Area of 5 magnitude since 1973, I have predicted all of them. Haven't missed one.
James Berkman doesn't monitor radio waves to predict earthquakes. He monitors ocean waves, tidal patterns outside the Golden Gate. Berkman, a geologist for Santa Clara County, says that when tides reach significantly higher than normal, an earthquake soon follows, because, he says, tides affect the Earth's crust.
As the tide comes in, it depresses the crust. The tide goes out, so the crust is going up and down with this load. A foot of water is 1 million tons per square mile. So anywhere along the seacoast and in the bay, you're subject to tremendous differential stresses.
In early January, he saw tides would be twice as high as normal, and he says he predicted up to a 6-magnitude quake would strike Southern California by January 16th. 4.5 hours into January 17th, the quake struck. Berkman says animal behavior is another indicator of a quake.
Between last Wednesday and last Friday, the missing dogs and the missing cats in the LA Times doubled.
And in Japan, Sakito Ueda has been detecting anomalous electromagnetic activity preceding numerous earthquakes and volcanic eruptions.
Beginning of the installation of the station. And as I said, when if you look at this, you can see there are some changes here. And it's not very clear here, but there's some change here, which is beyond the usual noise level. And here's a big one here. And here's another one.
Hello, I'm Bob Boy. I'm here at Ambient Research in Sausalito, California, and I'd like to tell you about an emerging technology that's being developed here, which allows early detection of earthquake signals days before the actual tremblors occur. These signals are detected in the background radio noise spectrum and are referred to as seismic radio precursors. But before we examine these signals, let's look a little bit at the evolution of radio technology. Since the inception of radio technology, many people had assumed that radio waves were purely an artificial phenomenon, an exclusive effect created by wizards in the laboratory. Later, in the 1930s, Carl G. Jansky discovered radio emissions coming from the Milky Way. Stars are now known to be gigantic radio transmitters, broadcasting a wide spectrum of electromagnetic radiation, EMR, ranging from low-frequency radio noise to gamma rays. So much for the artificiality of radio. Even in the 19th century, In the days of Edison and Nikola Tesla, lightning-induced radio noise was known to create recognizable propagation patterns. It was these patterns that Jansky was measuring when he discovered the cosmic radio noise. Tesla had even calculated the nearly correct resonant frequency of the Earth itself, and had postulated that electromagnetic waves of this frequency, 6 to 8 hertz, should be generated by the planet from the action of lightning. These Schumann resonances, as they became known, were in fact finally detected in the 1960s and may play a role in generating our seismic radio precursors. Other strange radio emissions were noticed at about the same time, a time when radio observatories were being built all around the planet. These observatories could receive and record a wide range and volume of EMRs. Before and during the Great Chilean earthquake of 1960, strange radio signals radiating from the earthquake zone were recorded at 6 of these widely scattered observatories. Years later, James Warwick of the University of Colorado compiled the recorded data and recognized the significance of the event.
The strangest thing happened in our data from Radio Astronomy Observatory in Boulder. Say 33 years ago. We were operating equipment at a number of places around the country, and in fact as far as Manila in the Pacific, New Mexico, south of Boulder, and Michigan, and a place near Ann Arbor. And on these different radio receivers, we recorded a 15-minute long period of greatly increased radio emission that was simultaneous at all 4 of the stations from which we were looking. The strange thing about it is that this radio emission was not interference, because it occurred simultaneously at different stations in many different parts of the country, in fact halfway across the Pacific as well. For a long time I was puzzled at what could have produced that radio emission, and really didn't understand its source. It was pretty clear that it had to be a large source, because it appeared on all of these radio receivers simultaneously. So I published the result in a journal article that just simply stated what the data were like and didn't offer very much of an explanation.
Earthquakes were broadcasting radio signals, but how?
About 15 years later, that would have made it 1975, a friend of mine who teaches at Stanford sent a letter out to me and I suppose hundreds or thousands of other astronomers in the world, and asked them if they had ever seen anything in their records that they didn't understand or couldn't identify. Well, he got back a bunch of responses from astronomers who had observed things in the sky that they didn't know what they were. And it set me to thinking, his letter set me to thinking as well, about what I had seen that was not really understood very well. And of course I thought of this event that had occurred in 1960. But in 15 years that had elapsed, a lot of new stuff had come out, and I had met different people working in different areas of science, in particular in geophysics. And as it just happened, it was a lucky coincidence, one of my friends had just come back in 1976 from a conference in Tokyo concerned with the prediction of earthquakes. And his experience at this meeting in Tokyo was that several research groups in the world, in particular in China, had made some very strange correlations with earthquakes. These were correlations between the activity of barnyard animals, chickens and ducks and dogs, the change in the level of water in wells, and even strange noises that appeared to the Chinese researchers to be related to earthquakes that subsequently occurred. So the Chinese made all of these observations, and in fact, on the basis of them, they predicted a very large earthquake that followed within a year of their prediction, and hundreds of thousands of people's lives were saved as a result of that successful prediction.
Other experimenters recorded similar effects in Japan, France, the United States, and the Soviet Union. In Greece, researchers were recording telluric current fluctuations preceding earthquakes. Telluric currents are natural electric currents found in the earth, generated by an electromagnetic interaction between the earth and the sun. Meanwhile, in 1979, Joe Tate, here at Ambient Research, was experimenting with methods of converting stray radio noise into usable electric power. He had developed a clock which drew its electrical power from an antenna that was a long piece of wire stretched out horizontally about 20 feet above the ground. The power supply for this clock worked something like the familiar crystal radio, except that it did not have a tuning circuit. Because of this, the crystal clock, as it was called, was able to utilize a wider spectrum of radio noise for the production of electric power. Its power supply was capable of delivering currents far in excess of what was developed in a crystal radio. In the early 80s, Tate demonstrated the clock to the late Frank Oppenheimer, founder and director of San Francisco's Exploratorium Science Museum. Oppenheimer suggested recording the power supply output over a long period of time to determine its reliability and dependability. After all, the device depended on whatever stray signals happened to be in the air. Using an Atari computer, which was donated to the museum, the power output from the clock was measured continuously and recorded on floppy disk. This was accomplished by simply disconnecting the voltage regulator in the clock and plugging the resulting fluctuating voltage into the joystick port of the computer. This little power supply has become known as the Ambient Power Module, the APM, because it derives its power from ambient background radio noise. This small printed circuit board, when connected to antenna and ground, can deliver small amounts of power continuously. As the recorded data were studied, however, patterns of small daily fluctuations were noticed. These patterns were different at each location tested, but were consistent over long periods of time. All well and good. The APM looked like a very dependable source of power, until a nearby earthquake in 1984 anyway. On April 24, 1984, a 6.0 magnitude earthquake struck about 90 miles from the Sausalito APM recording station. Days later, while looking through the data, it was noticed that the APM output had dropped to less than half its normal value for several hours during the afternoon 6 days before the earthquake. This was very peculiar because most of the APM's power was received from broadcasting stations, and broadcasting stations hadn't done anything different that afternoon. Apparently something had temporarily decreased or depressed the propagation of radio waves. At high frequencies, such effects can be caused by atmospheric conditions. The lower frequencies involved here would not be as subject to these effects, particularly signals from local radio stations, which were the strongest and account for most of the power. It was tempting to think that this strange radio depression might somehow have been a precursor to the earthquake. Several smaller quakes had occurred in the area during the year before. Perhaps these also were preceded by similar radio anomalies. Looking back through the accumulated radio noise data, smaller, less noticeable radio depressions were found which occurred prior to the lesser earthquakes. Tate called the United States Geologic Survey Office and told them about the events. He was told about various reports from ham operators in the area, radio noise events accompanying earthquakes, but no one had recorded them. Jack Everenden, who handled the matter at USGS, requested copies of Tate's data, which was sent. A short time later, Tate was asked to team up with Dr. William Daly at Lawrence Livermore Lab in an effort to gather radio noise data along the San Andreas Fault in California. For the next 3 years, they deployed several radio noise recorders along the San Andreas Fault, from San Francisco to San Diego. These units were battery-powered paper chart recorders which could hold 1 month's data. They recorded on 3 bandwidths, 0.2 to 1 kilohertz, 1 to 10 kilohertz, and 10 to 100 kilohertz. In addition, they continued using the APM recorders in 2 locations, Sausalito and San Mateo. During this period, there were some 46 earthquakes 4.0 magnitude and above, which occurred within 120 miles of one of the stations. Of these, 32 earthquakes were preceded by a radio anomaly. Only 14 quakes occurred which were not preceded by radio precursors, and none of these was above magnitude 4.2. There were also 10 false positives, radio events with no quakes. These may have been caused by earthquake preparation forces which failed to mature, although there is evidence of instrument failure in most of these. Either way, the score was about 70% of the earthquakes preceded by seismic radio precursors. The results of the study were published in Physics of the Earth and Planetary Interiors, October 1989, just as the Loma Prieta earthquake struck Northern California. By this time, the USGS had dismantled their network of recording stations. However, one of the original APM recorders was still running at Tate's lab in Sausalito, California. This instrument recorded the largest radio depression seen throughout the entire study about 60 days prior to the October 17 shock. It is curious to note, by studying several smaller earthquakes from 1985 to 1987, that the larger the earthquake, the larger and earlier the precursors appeared. The 6.0 earthquake of April 1984 was preceded by a radio depression 6 days before the shock. The Loma Prieta earthquake of about 7.0 magnitude was preceded by a much greater radio depression 60 days before. A 7.0 magnitude quake is 10 times greater than a 6.0. The 60-day precursor time for the 7.0 earthquake was exactly 10 times the precursor time for the 6.0 earthquake. More data, however, is needed to clarify this relationship. And now, I'd like to introduce to you the principal investigator at Ambient Research, Mr. Joe Tate. Joe?
Thanks, Bob. I'd like to show you some of the equipment we use here for detecting seismic precursors. This is the background radio noise detector that we operate here at Ambient Research. And what we're looking at here is the last 24 hours of data that we've recorded from an antenna. The antenna goes to a detector. The detector converts the stray electromagnetic radiation, or radio noise, into usable electric power. You see this is in volts here. We're running right about 6 volts right now, and it'll stay in that general area most of the time. It sort of varies inversely with the tides here, one of the strange things that we discovered. And How this project got started, we were actually made a device for recycling radio noise. And what it does is it uses the antenna to pick up any frequency noise and convert it into usable electricity. We were using this to power up small devices like clocks and calculators. And what we did, we used this computer for performance testing the power supply and found that just before earthquakes, the power supply became very undependable.
Mm-hmm.
This was a completely unexpected result, and we wondered, what kind of an event could affect total background radio noise that much. And its juxtaposition to the earthquake made us suspect that the two events might be related. When we checked back through our previous data, we found that other smaller earthquakes in the area were also preceded by these type of events, although they were smaller. Since then, we've recorded probably 20 or 30 other events of the same type, all preceding earthquakes in our area. And so we've come to think of these things as seismic precursors that could in fact be used to predict our local earthquakes.
Okay, I want to show you the antenna system. It's this attached to this pole. It's a long wire antenna, and it comes down and attaches to this box here, which is the actual detector. This detector converts the radio noise into usable DC current, which is fed through this coaxial cable to a computer inside the lab.
Warwick's lab experiments showed that fracturing rocks did generate radio waves. While crushing westerly granite in a shielded space, a receiving antenna detected broadband radio signals ranging from 500 kilohertz to 30 megahertz. Most of this energy was concentrated at the lower frequencies. Other experimenters have also been measuring changes in the electrical resistance of rocks under the influence of great pressure. During the 1970s, William Brace of MIT compressed various rocks in a powerful press while recording their resistance. His findings show that as rocks approach fracture pressure, they become much more conductive. A related experiment by William Daly at Lawrence Livermore Lab subjected rocks to evenly distributed hydrostatic pressure while also recording their electrical resistance. Under these conditions, the rocks did not show the significant resistance change shown by the rocks in Brace's press. Apparently, the uneven stresses developed by pressing on two ends of the rock were responsible for the resistance fluctuations. Although Warwick's experiment showed rocks could emit radio waves during crushing, calculations showed that any such waves generated far underground would be absorbed in the earth, never reaching the surface with enough energy to be detected in the atmosphere. In addition, this concept could not account for the radio depressions which were being observed by Joe Tate and others. Takeo Yoshino of the University of Electrocommunications in Tokyo has proposed that resistance slots form along a fault line due to effects similar to those demonstrated by Brace's experiment. Yoshino argues that if ground resistance becomes high enough in these slots, then radio waves could pass through them as easily as they pass through the atmosphere. It would also mean atmospheric radio waves could pass into the Earth. This would create interesting resonant effects. Could ground resistance actually reach the values required to sustain such an effect? The groundwater alone would render the strata quite conductive. However, C.B. Raleigh of USGS has calculated that frictional heating during the earthquake preparation process would be sufficient to boil the water out of the rupture zone. Perhaps this effect could combine with stress-induced rock resistance fluctuations to create high-resistance electrical slots in the Earth's crust. Based on this idea, Joe Tate believes seismic radio precursors recorded by ambient research and others are the result of fluctuations in the ground radio absorption rate. Radio waves propagating through the atmosphere are always being partially absorbed into the ground. The absorption rate varies from place to place, but is based on the conductance of the ground as well as the distribution of rocks and sediments. If anything alters this equilibrium, radio intensity in the atmosphere will also change. For instance, a higher ground absorption rate will result in a lower intensity in the atmosphere. The reverse would also hold true. A loss of absorption will result in increased atmospheric intensity. Seismic radio emissions may actually result from this effect. As a model for explaining seismic radio anomalies, this has some advantage, explaining both seismic radio emissions and depressions. It would also explain the telluric current earthquake precursors recorded in Greece. As ground conductance changes, electric currents flowing through the earth would be diverted to zones of higher conductance.
I want to thank Brian Brady of the U.S. Bureau of Mines for the use of his photos of his rock crushing experiments. His experiments recorded the emission of visible light during rock fracture. So we see that fracturing rocks emit not only radio waves, but visible light, another part of the electromagnetic spectrum. After the publication of our paper, Evidence of Electroseismic Phenomenon, I attended a National Science Foundation conference on electrical precursors at Lake Arrowhead in Southern California in June 1992. This conference was attended by 50 of the world's leading scientists in the field, including Barazos, Alexopoulos, Nikopoulos, the Van Group, so-called Van Group from Greece, who have been so successful in predicting earthquakes using telluric current measurements. Also at the conference was Tony Fraser Smith of Stanford University, whose group successfully recorded electromagnetic anomalies preceding the Loma Prieta earthquake. Some of these anomalies were coincidental with the anomalies that we measured prior to the Loma Prieta earthquake. My talk was on ground conductance and radio absorption. I argued that pre-quake ground conductance fluctuations could alter the ground radio absorption rate, giving rise to the anomalous radio events observed by us and others. These ground conductance fluctuations could also give rise to telluric current precursors and also ULF magnetic precursors. Earth currents would be diverted to zones of higher conductance, and the magnetic and electrostatic rate of absorption would fluctuate. My ideas were met with skepticism at the Lake Arrowhead conference, but since then, the group at Stanford has done some theoretical calculations to test this idea. Simon Klemperer explains their work.
Very anomalous signals immediately before the earthquake. The background field increased to 10 times 12 days before the earthquake, and to 100 times just a few hours before the earthquake. The work that I am doing with my co-author, Moshe Mertzer from Israel, is to try and produce a model, a geological model of the earthquake process that can explain these anomalies. And the work that we present at this meeting will describe a physical model in which we calculate anomalies shown here in these red crosses that appropriately describe the anomalies that were recorded before the earthquake. It's an attempt to describe the earthquake fault as a conductive zone in the crust that can act as an antenna reflecting magnetic field energy back to the recorder that Tony was operating. We know from the aftershock pattern of the Loma Prieta fault, the earthquake extends to 18 kilometers depth, about 4 kilometers wide. We know from conductivity measurements made before the earthquake that there is a conductive zone reaching also 10 to 20 kilometers deep in the earth. And we simply have prepared a mathematical model of the fault in a gross simplification as an elliptical conductive zone extending to 18 kilometers and 4.5 kilometers wide. We regard this as the background geometry before the earthquake occurred or before any preparation for the earthquake began. We have then calculated a model in which we increase the conductivity of this zone appropriately to reflect sufficient magnetic energy to be recorded and give rise to the anomalies described by Tony Fraser Smith. And very simplistically, what we are proposing is that if microcracks develop in the days and hours before an earthquake, they can redistribute a fixed amount of fluid within the fault zone, so giving rise to a more conductive structure. we're suggesting that prior to the fault, prior to the earthquake, there is significant water trapped in the fault, but in a relatively non-conductive geometry where all the faults are sealed to each other. In the incipient deformation phase, 12 days before the earthquake, we're predicting that microcracks begin to form, that are long, narrow cracks open up and allow fluid to become linked in connected pathways. And we predict that this increase in conductivity in the fault zone will give rise to the enhanced magnetic field anomalies reported by Tony Fraser-Smith.
Takeo Yoshino's concept that resistance slots form in the Earth prior to earthquakes was a good idea. But we now know from the evidence that just the opposite is true. Klemperer, who just spoke, has told us that conductance probably goes up in the fault zone prior to earthquake. And we know also from William Brace's laboratory experiments that as rocks approach fracture pressure, their conductance is increased. But what actually happens in the field? Jean Chu of MIT is now going to tell us about what Chinese researchers have been doing for the past 25 years in gathering ground resistance measurements prior to earthquakes in China.
What China has done is, over the last 26 years, it has been collecting data in many, many different disciplines. And one of these disciplines is in geoelectric signals, or electrical measurements. And what I show here is a system that China has set up that's spread throughout the country. And it's about 110 stations. They're geoelectric stations. And what they mainly monitor are two methods, that's resistivity and self-potential. And what I'll be showing you and discussing here today and tomorrow in the paper is resistivity measurements. Note that on this particular map I also show the seismicity. This is for events within mainland China of events greater than magnitude 5. And this is over the last 26 years, the same time span that the geoelectric system has been deployed. And as you see, the stations were set up more or less in following the zones of seismic activity. And I'll bring your attention to this area, the Beijing-Tianjin area. And in 1976, there was a large magnitude 7.8 earthquake where 240,000 people perished. This is the trace for the Tangshan earthquake, and it was taken at a geoelectric station called Changli, 70 kilometers from Tangshan. Across the nation, 1,500 kilometers away in a completely different setting, on the edge of the Tibet Plateau. This one is by the ocean. There was a little town or city called Sunpan, and that area had a earthquake, two of them, in fact, a week apart. And it was the same year, but it was in August. And so these two events were monitored by, or rather there's a station called Wudu, in the town of Wudu, 100 kilometers away from the epicenter area. And this is the record they have over the years' time. So if you go ahead and superimpose these two records, about the event time, again, these are two different events, two different parts of China. You get the records superimposing in a remarkably similar way.
Let's take another look at Jean Chu's chart here of electrical ground resistance before the Tangshan earthquake of 1976. Here's the time of the earthquake, right here, and you see that the ground conductance is going way up. This is resistance going this way, this is conductance going down. And at the time of the earthquake, it reaches its lowest peak, or highest peak of conductance. Notice also that there's several spikes here. They come right before the earthquake. These spikes here are probably the cause of the seismic radio precursors that we see, in which we see reduced radio noise in the atmosphere. Notice here there's a spike that goes up. These might be responsible for some of the so-called radio emissions that we've seen preceding earthquakes, and that really are not emissions per se, but are actually a loss of ground radio absorption that makes it look like the background noise has gone up. Let's look again at the Tangshan earthquake. 30 days prior to the earthquake, there was a conductance spike here that we discussed before, and which lasted, actually two of them there, each of which lasted less than a day. Compare this to an event in California, a radio depression that occurred 30 days prior to the Loma Prieta earthquake and which lasted about 12 hours. This event may have been caused by a change in ground conductance that caused greater absorption of radio waves into the ground. These data were compiled by Thi Kien and Yulin Zhao of the Beijing Institute of Geophysics and are the result of 25 years of monitoring at hundreds of stations throughout China. With this data, they were able to construct conductance charts which clearly show conductance slots forming in the earthquake zone. Here we see the formation of such a slot from 31 months before the Tangshan earthquake, continuing until 1 month before the quake, when the slot is most pronounced. 5 months after the quake, the slot disappeared. Solid evidence of ground conductance earthquake precursors. Obviously, there are a number of different phenomena that can be monitored to detect earthquake precursors, but one that we feel needs more study is ultra-low frequency magnetic noise anomalies, recently cited by Tony Fraser Smith. We've been experimenting with this technique ourselves, and I'd like to tell you a little bit about our system.
This is the ultra-low frequency magnetic detector that we operate here at Ambient Research. This detects magnetic signals in the 0 to 16 hertz range, which includes the Schumann resonances. These are caused by the planet itself resonating due to the action of lightning. We use a magnetic detector. It consists of a coil of wire wrapped on a soft iron core in a double shielded housing and suspended 10 feet below water. And this helps to shield out a lot of the cultural noise that we don't want to pick up. And it comes up here and is connected to a preamplifier right here and a notch filter. The output's displayed here on the spectrum analyzer. This work was done probably first by Herb Werner in the 1940s while he was working for Ford Aerospace Company. His work was classified by the U.S. government, and I believe that it remains classified to this day, and probably explains why, when various researchers stumble onto this from time to time, they are ignored by the government scientific establishment.
In spite of these ruminations, I knew it must be possible to build a machine that could automatically detect seismic electric precursor signals and set off some sort of alarm. I called engineer David Brown and asked him, given the nature of the signals, how could we build a seismic early warning system? David began by altering the old APM recorder system, writing in an algorithm that allowed the computer to recognize events and set off an alarm if certain patterns occur. This alarm was tested and went off properly days before a dozen earthquakes near the Bay Area over a 2-year period. Now I'd like to introduce you to David Brown, who will tell us more about the seismic early warning system. Dave?
Thanks, Joe. What you've said so far pretty much describes the state of our system as it stands at the moment. We applied for and received a patent for a seismic early warning system which operates by monitoring the background radio noise spectrum. As Joe has explained, these signals are caused by fundamental changes in the electrical properties of the fault zone. Other methods of detecting the events are available, such as monitoring telluric currents. But our radio monitoring method is simpler to achieve and does not require the extensive array of ground probes needed to monitor the actual ground conductance fluctuations. What really is needed, though, to do this work comprehensively is a system that can monitor all of the principal parameters simultaneously. By this, I mean a system which can monitor ULF magnetic noise, telluric currents, and background radio noise. Okay, we're now going to put up on the screen the system that we've just been talking about. Could you get the lights, please? Okay, on the screen here, you see the 3 types of systems that we're going to be using in this comprehensive system. Here is the APM monitor, which we've been using up to this point. The antenna feeds the APM, as Joe explained earlier. This goes to an analog to digital converter, which is driven by a clock, and the output of the ADC goes into the CPU. Second, we have a ULF magnetic monitor, which is a coil. Joe described that earlier in the system at the bottom of the bay. This is the antenna for that. That feeds ADC2 and also goes into another port of the CPU.
Then we have two sets of telluric current probes feeding two analog to digital converters and going into two more ports of the CPU. The entire program that runs all of this and samples the different inputs is run by a program which is in EEPROM here, and there's a random access memory here that's used to store data. We have a display that can display any of the various parameters we want. Everything is recorded ultimately on a disk drive, and we also have printout available of any of the parameters that we're looking at. There's a hex keyboard and keyboard encoder that's used to input instructions, and this entire any of the data in the CPU can be output through a modem, and there's a transmitter or a dialer, auto dialer, that can be used to transmit this information to other stations in the system or any other location that we need to transmit data to. By using this entire system, we can then keep track simultaneously of the three different parameters: the APM, the ULF monitor, and the telluric current probes.
The telluric current probes can also be used for ground conductance measurements with the addition of program instructions. The available data from Greece and China indicate telluric current monitoring is more sensitive. The conductance precursors in China were deviations of only a few percentage points, while telluric fluctuations recorded in Greece amounted to 100% and more deviations. For our ULF monitoring section, I propose a different approach to tracking events. Instead of merely measuring the amplitudes of selected frequencies, we should use our microprocessor to calculate the spectral fluctuation envelope. Looking at this chart, frequency and amplitude are plotted for two spectra. Increasing frequency is to the right and increasing amplitude is vertical. Each frequency has a corresponding amplitude for both spectra. A theoretical baseline spectra and an anomalous spectra of lower power are plotted here to simulate a ULF magnetic event. The area between the spectral plots represents the actual difference in power and is the spectral fluctuation envelope. It can be calculated by taking the sum of the difference in amplitude for each frequency sampled. Looking back at the chart from our APM recorder, we say that each point along this radio depression could be used to calculate the spectral fluctuation envelope by subtracting it from baseline and writing the answer in power, which is calculated from the circuit impedance and the recorded voltage. So each variation on the APM plot has a related spectral fluctuation envelope. Since each spectral fluctuation envelope represents power, the area inside this radio depression represents energy, which can also be calculated and therefore provide some uniform measure of the events themselves. The microprocessor-based system can develop and analyze these parameters continuously, giving instant alert to changes in geologic conditions that otherwise would go undetected. As more data comes in, we'll understand more about this phenomenon. In the meantime, we're regulated by the frequency of large earthquakes. Nevertheless, we're within reaching distance of being able to give warnings in the days before the actual shocks.